Alrighty, we're going to talk about alkene reactions in this video. It's going to be kind of a part one of part two of two parts. So this one, we're just going to talk about the three reactions that I have listed out here. We will talk about more later, but these are the ones we're going to start with. So the things we need to keep in mind with alkene reactions is that those alkenes are more electron rich, and they are also weaker and easier to break than a sigma bond is. So we're going to see them react with acids and electrophiles, that kind of thing. We're also going to see alkenes participate in addition reactions where the sigma bond is lost and replaced by two new sigma bonds. So it's different than the reactions we talked about so far, where we've got substitution, we've got elimination, we've got acids and bases. And this is going to be adding something to your structure. So we're not taking anything away. We're not replacing anything. All we're doing is adding two new sigma bonds to the structure. So I'm going to start with the one on the right. So this is hydrogen and palladium on carbon. So the hydrogen here is what we're actually going to be adding to our structure. And all it is it really is just taking an alkene to an alkane. Okay, so if we think about what hydrogens we have here, we've got HA, HB, and I don't have anything on the other side, so I've got an H here now. I now have HC. And we're going to add those. Okay, so we've added two H's to the alkene, making it no longer an alkene anymore. So that is called a hydrogenation. So a hydrogenation, the name is in, the key is in the name here. We're adding hydrogen to the alkene. All right, so let's go to the one on the bottom. So this is sulfuric acid and water. You can also use alcohols here if you want to add carbons to your molecule. So if I did it with just water, I'm going to be adding water across the double bond. Okay, so my water, let's do a different color here. Ended up here and here. Okay, so we've added water across the double bond. If I do it with alcohol, I'd get the same thing except an RO where my OH is. So something like that. Okay, so that's a way of making alcohols out of alkenes or ethers out of alkenes. And then this last one, we've got HX. So in this case, we're going to have an H on one side and our X on the other side. Like that. Okay, so in all of these cases, we have things to think about in terms of regiochemistry and stereochemistry. So we'll see why we have particular regiochemistry when we go through the mechanisms. But the thing I want you to think about is, why did I pick this particular carbon to put, my alcohol on, to put my my halogen on? How did I end up making those decisions? All right, and I should have specified over here. So this is a hydrohalogenation. Okay, so hydrogen, halogen, right? Kind of split apart the word. this is a hydration because we're adding water. Okay. I don't actually know what the one with alcohol would be called, but they probably still call it hydration anyways. Okay, so we have those three reactions. So let's look at the mechanisms of these. So I'm going to actually start with the hydrogenation mechanism because it's kind of a little different. And then the other two are more related. All right, so for hydrogenation, what we have is we've got our starting material, we've got hydrogen, and we've got palladium on carbon, okay? So if I've got palladium on carbon, that's a catalyst. Okay, it makes the reaction go much, much easier. So you have hydrogen gas, you've got palladium, that's gonna lower, it's gonna create a different pathway to travel that's gonna have a much lower energy of activation than if we just pumped hydrogen gas at this molecule. So the way that this works is we've got palladium as a surface, right? The palladium is going to be a metal. It's going to just be sitting on the surface of carbon. So carbon, like, it's essentially like charcoal. It's very, very black when you look at this in the bottle. So what happens is as you add hydrogen gas to this, you end up getting hydrogen gas split and peppered on your surface. Okay, so the hydrogen gas is going to split into hydrogen atoms and deposit itself on the surface of the palladium. So then your alkene is going to come along. So here's our alkene. Actually, let me try that again. I'm going to draw the alkene first and then. Okay, so then I have my alkene come along. These H's are pretty activated because we've got, what did that erase? Because we've got our palladium activating them. So our alkene is going to go grab an H that can give the electrons back to the palladium. And then another H is going to go and attack the other side of the alkene. So that's how we get it on both sides. And if we think about how this approach is all happening, essentially what happens is you've got your flat alkene and then our H's sticking up on a surface. So we're going to add our H's this way. You could also imagine your alkene coming and adding the other side, but in both cases, your hydrogens are coming from the same place, okay? So that means that they're going to get added syn on your structure. Oops. I'm trying to draw this as, actually, I know how to do this. Okay, so what you're going to be left with are these two H's adding syn to each other. Okay, so they're going to be on the same side from this addition. Okay. So in this particular example, it doesn't matter a ton because I'm not forming any stereocenters here. Okay, so if we had a reaction where we did have stereocenters, then we would see syn addition of those two H's. All right, so then let's look at the hydration reaction. So this is using reagents that we are a little bit more familiar with. So hopefully, once we've been working with these things for so much, you can kind of guess what the first step might be. If we are in an acid, the first step is going to be protonation. And we have sulfuric acid around. Okay, so if we're trying to think about what are we going to protonate, this is an acid. The alkene is going to be our base. Okay, so we're going to have this alkene go grab the H, give the electrons to the oxygen. So if I'm using my alkene as a base here, then I have some things to consider. I just realized I didn't put my label on there. Okay, so we are going to be adding an H to one side. But I really need two bonds if that is going to be neutral. So I can either add my H here, which would mean that that carbon is lacking in electrons. So remember, I've got H, H. HH. Or I can add my hydrogen over here and get that carbocation. So at some point, I have to form a carbocation, because if I'm only doing these arrows, I'm using the 2 electrons in the pi bond to go get to protonate, then I can only add the H to one side, and there are 2 carbons involved in that pi bond. So that means that one of them is going to get electrons ripped away from it. So which one would rather have electrons ripped away? This is making a primary carbocation. This is making a tertiary carbocation. So we won't form this one. This one is happy, that one is sad. Okay, so if it helps you to draw out both options and then identify which one is best, that's totally fine. So we're going to move forward with the tertiary carbocation. And just like we've seen before, once we use sulfuric acid to protonate, it's pretty much not coming back in again. So in this case, I've got water that is going to be my nucleophile. So now I no longer have an alkene. So at this point, electrophile, nucleophile, pretty much just like an SN1 reaction. Okay, so we're going to attack that carbocation. Okay, then I have the protonated form here. Then I have another molecule of water come around, deprotonate that to get to a neutral product. Okay, so if we kind of summarize this is all using chemistry that you've pretty much seen before, right? The first step is an acid-base reaction, and then the second step is an SN1, right? Okay, so the other thing that we need to be wary of is we need to watch for rearrangements. Okay, that's something that's very, very important in this process. Excuse me, is that since we're forming a carbocation, we absolutely can have rearrangement occur. Okay, the other thing is that the stereochemistry is not really possible with carbocations. So all the same stereochemistry rules for all of our any like carbocation type reaction is going to be the exact same for this. Okay, in this case, this is achiral. So we don't really have an issue of what's going on with the stereochemistry, but you're going to have the exact same situation of if you're forming a stereocenter. That again. It is going to be racemized, okay, including if you're forming a stereocenter at this first acid-base reaction. So if the first thing when you protonate forms a stereocenter right here, then you will end up having that be wedge and dash because you're still starting with something flat, okay? So just keep that in mind as you're going through these reactions. If I'm starting with something flat, I have equal opportunity of top and bottom reaction. Alrighty, so let's do the last one. And I guess let me add in my H. And what color did we use? Pink. Okay. Ooh, my cat just, oh my, hi. Hi Penny, what's up? So let's do the hydrogenation next. She's got the zoomies. I heard her run from downstairs, from upstairs. So we've got hydrogenation. So let's do the same thing here. And let's just do it with HCl. Why not? Okay, so we've got HCl. Hopefully this is kind of reminiscent of what we've already talked about again. So I've got a strong acid. I've got my alkene, which we've already seen act as a base. So my first step is going to be protonating that alkene. So this is my base. This is my acid. Again, I have to make that choice of which side is my H going to go on. So again, I could put it here, which means my carbocation's over on this side. Or I can put it on the other side. To put my carbocation there. So again, I've got a primary here. That's sad. I've got a tertiary here. That's happy. And so if I'm not moving forward with this, then we always need to ask ourselves, is there any rearrangement possible? In this case, I could move it to a secondary, or the primary. None of those are better than a tertiary, so I don't have any rearrangement here. And I have formed Cl minus. So we've seen in the alcohol reaction particularly that we just went over, we've seen once you protonate with something like HCl, HBr, or HI, we've seen that you can end up making a good nucleophile afterwards. And that's exactly what's going to happen here. We're going to go and attack that carbocation with our new nucleophile. Oh. should have done the arrow over here. So then I get to that product, okay? So this is pretty much an SN1 as well, right? So always look for rearrangement. Think about what's happening with the stereochemistry. In this case, again, I have an achiral product, so I didn't have to worry about the stereochemistry too much. So that's what the reaction is like. So hopefully this isn't a huge leap. Really the new part is doing an acid-base reaction of an alkene, and then of course our hydrogenation, which is a little bit different. But always ask questions. We'll cover this a little bit on Tuesday as well and do some practice on it. So have a good one, everybody, and I will see you all later.